Welcome to Joe's Classroom and the lecture series on frequency domain analysis. In the last three lectures, we understood the basics of Bode plot, taking systems with poles or zeros at origin, poles or zeros on the real axis other than the origin, and complex poles or zeros. Now we are going to take a break from these lectures and are going to work out a few tutorial problems on sketching this Bode plot. And here we are going to take systems with transfer functions having combinations of all these terms I mentioned now. Since this tutorial needs a few fundamentals that we learned in the previous lectures, let us quickly review them. We started with systems with poles or zeros at origin, and these are the transfer functions, and this is going to be the pole zero plot. If there are poles at the origin, then the Bode magnitude plot is going to be a straight line with a slope of minus 20 n decibels per decade, where n is the number of poles at the origin, and it will be passing through 1 comma 20 log k, where k is the open loop gain. And if it is a system with zeros at the origin, then the line is going to be an increasing line with a slope of 20 n decibels per decade, and this line will also go through 1 comma 20 log k. In the case of poles, the phase plot is going to be a horizontal straight line at minus 90 n degrees, whereas in the case of origin, it is going to be at plus 90 n degrees. And if you take the systems with non-zero real poles, that is the poles lying on the real axis, poles or zeros lying on the real axis. If we take only the poles, then the transfer function is going to be like this, and it is going to have the first order terms. And these first order terms will be appearing at the denominator. In such case, the Bode magnitude plot will have a pair of straight lines. One straight line is going to be a horizontal line at 20 log k, and another straight line with a slope of minus 20 n decibels per decade. And the phase plot is going to start from 0 and it is going to end at minus 90 n degrees. And we came across something called corner frequency. Corner frequency is the frequency at which the asymptotes of the exact Bode plot intersect, and therefore we get the asymptotic Bode plot as well as the exact Bode plot. If the system is having some non-zero zeros, I mean the zeros on the real axis, okay, then it is going to be very similar to the case of poles. Only thing is the second line in the pair is going to have plus 20 n decibels per decade. Otherwise, everything is going to be the same. And even here, the frequency, I mean the corner frequency, will see a change in the slope. And as far as the phase plot is concerned, it starts from 0 degree and reaches 90 n degrees as the frequency increases from 0 to infinity. And if you take systems with complex poles, this is going to be the pole zero plot. In that case, again, we are going to have a similar structure as we had for systems with poles on the real axis. But here the only difference is the second line will have a slope of minus 40 n decibels per decade. So if it is a system with n is equal to 1, the slope is going to be minus 40 decibels per decade. And the corner frequency here is nothing but the natural frequency of oscillation. And if the system is going to have complex zeros, then we will have the same asymptotic plot, but only difference is, this line will be an increasing line with a slope of plus 40 decibels per decade. And in the case of poles, the phase plot starts from 0 and ends at minus 180 degree, where in the case of zeros, it will be starting from 0 and it will end at plus 180 degree. So this is what is the short review of what we learned in the previous three lectures. If you want to have more details, I would request you to go through three lectures, that is Bode plot part 1, part 2 and part 3. Please note a very important point. We are going to consider only the minimum phase systems. Minimum phase systems are systems whose open loop transfer functions will have their poles and zeros on the left of the S-plane. Having reviewed the basics, we will take up three examples for this tutorial. The first example I will explain in details using the principles what we learned from the three lectures. And from the explanation, we will develop a step-by-step procedure to sketch the Bode plot for any given transfer function. And we will be using the set of set step by step procedure developed using this example 1. We will sketch the Bode plot of the transfer function given in example 2, and the example 3 will be given as an exercise explaining the basic preliminary things. Let us take the first example. From the previous lectures, you should be knowing that the first thing what we need to do in sketching the Bode plot is to convert the given transfer function into time constant form. Obviously, this is in pole zero form because the S term is having a coefficient of 1. So therefore, it is necessary to convert this transfer function into time constant form. To convert it into time constant form, this constants in these first order terms have to be made as 1. For that, I have to take 80 out of these two terms and 2 out of these two terms. If I do this, this is what I get. Now all these three constants I can combine together, and 1 by 80 is 0.0125 and 1 by 2 is 0.5. So I get the same transfer function in a time constant form. So here the k value is 6.667. But if I look at this transfer function, I'm not very happy because this is not in, if I look at it together, this is not in any standard form. But at the same time, if I look at in this way, this is a very familiar term to me. This is k by s, and this is also familiar to me. This is 1 plus ts, and this is also familiar. This is 1 by 1 plus ts. So I can very well write the given transfer function in this way. This looks beautiful because I'm very much familiar with this, these structures. Now, to find out or to sketch the Bode plot, I need to find out g of j omega. I just get g of j omega by replacing all these s terms by j omega. And also we know that to sketch the Bode plot, the gain has to be found and the gain has to be converted to decibels. So if I convert the magnitude of g of j omega into decibels, this is what is the expression. And since I'm going to take the logarithm on the magnitude of all these terms, these multiplications are going to become additions. So therefore, the magnitude of g of j omega in decibels is given by 20 log of magnitude of this plus 20 log of magnitude of this function and 20 log of magnitude of this function. All the magnitudes in decibels have to be added together. So this makes my job easier because here it was multiplication, but when I converted this into decibels, all the multiplications became additions. So what I understand is if I could plot this gain in decibels, and if I could plot this gain also in decibels, and if I could plot this gain also in decibels, then the total gain of g of j omega in decibels is going to be, addition of these three. So in other ways, I can say that, see, this plot, this magnitude was generated by this transfer function, and this magnitude was generated by this transfer function, and this magnitude was generated by this term. Then what I understand is the magnitude plot of g of s is going to be the addition of the magnitude plots of these three terms. So what I can do is take these three terms separately, plot their magnitude plots in decibels, and add them together. So if I'm interested in asymptotic Bode plot, draw the asymptotic Bode plot for Bode magnitude plot for this, Bode magnitude plot for this, asymptotic Bode magnitude plot for this. Then take an addition of all these magnitude plots, three magnitude plots, and you get the answer. So that's what we are going to do. So let us take these three terms separately. Okay. So let me take the first term. Obviously, this is an integrator with a single pole at the origin, and this is going to have a decreasing straight line. Since n is equal to 1, the decreasing straight line will have a slope of minus 20 decibels per decade, and it will be passing through 1 comma 20 log k. K is 6.667, and you have to take 20 log k. So therefore, this term will result in a magnitude plot like this. See, the slope is minus 20 decibels per decade, and it passes through 1 comma 16.48, which is nothing but 20 log of k, that is 6.667. That's done. Now we consider the second term. So this is of the form k by 1 plus ts the whole power n, where k is 1 and n is also equal to 1 and t is equal to 0.5. And this is a first order term, therefore, or it is a term resulting in a pole at the real axis. And if I draw the magnitude plot for this, there will be a pair of lines with a corner frequency. The corner frequency is given by 1 by 0.5. Okay, 1 by t is the corner frequency. For frequencies lower than the corner frequency, the magnitude is going to be 20 log k. And for frequencies greater than the corner frequency, the slope is going to be, n is equal to 1, therefore minus 20 n decibels per decade. Why minus comes? Yeah, it comes in the denominator. Okay, it contributes to a pole, and therefore the slope is going to be negative. So I can plot. So this is the corner frequency that is given by 1 by 0.5, and up to this corner frequency it is going to be a straight line with 20 log k. K is equal to 1, therefore 0 decibels, 20 log k. And beyond this corner frequency it is going to be a straight line with minus 20 n. N is equal to 1, therefore minus 20 decibels per decade. Clear. Now let us take the third term. So of course it is very similar to this. Only thing is it is there in the numerator, and therefore up to the corner frequency of 1 by 0.0152, sorry, 1 by 0.0125, that is, which is equal to 80 radians per second. Up to that point it is going to be 20 log k. Again k is 1 here, so therefore 20 log k will be 0. So therefore up to this corner frequency the magnitude is 0 decibels, and beyond the corner frequency, since this is a numerator term, the slope will be plus 20 decibels per decade. Now, as I said, to get the Bode magnitude plot for this entire transfer function, it is just sufficient to add these three plots. Yeah. So this is the space where we are going to sketch the asymptotic Bode magnitude plot for this transfer function. Let us see. So there are two corner frequencies corresponding to these two first order terms, and the one corner frequency is it is at 1 by 0.5, that is equal to 2. This is 1 and this is 2, and this is another corner frequency which is uh, 80. So this is 10 and this is going to be 80. So the corner frequencies are marked. If you look at this term up to this corner frequency, the third term doesn't contribute anything. The gain contribution is 0. Okay, so therefore if I want to if you want to sketch the Bode magnitude plot before this second corner frequency, I need not consider this. I need to consider only the first two terms, just add their magnitudes. Now let us come to this first corner frequency. Up to this first corner frequency, the contribution by second term is 0. Not only the third term contribution is 0 already, and the second term contribution is also 0 decibels up to this, the first corner frequency. And therefore, if I need to sum up the magnitudes for frequencies lower than the first corner frequency, I need to consider, only the first term. Therefore, I can conclude that before or for frequencies lower than the first corner frequency, only contribution to the gain is from the integrator term in this case, or this term contains the constant gain and the integrator term. So the general point of observation is, for all frequencies lower than the first corner frequency, the contribution is from the constant gain, integrator, and similarly the differentiator. So I can say the contribution is from the constant gain, integrator, or the differentiator. Okay, S term in the numerator, that can also contribute. So I have to take only that part. So the same thing, same line I have to sketch here up to this corner frequency omega C1. Yeah, the same line sketched here. So this line is valid only up to this first corner frequency. Now, between the first corner frequency and the second corner frequency, in this section, the contribution is from the first term and the second term. If you look at this first term, it is going to decrease as in the same way, and the second term is going to have a slope of minus 20 decibels per decade. And the first one is also having a minus 20 decibels per decade of slope. So therefore, obviously in the second section, the slope of the line is going to be minus 20 plus minus 20, that is minus 40 decibels per decade. So the line is going to start from this point, and the line will have a slope of minus 40 decibels per decade. Okay, so go to one decade, come down by 40 decibels, mark the point, connect it. Okay, yeah, you got a point, you got a line with minus 40 decibels per decade. And beyond this corner frequency omega C2, the contribution is from all these terms. Okay, so but if I look here, it is the slope is minus 20 decibels per decade, here it is minus 20, here it is plus 20. So therefore the net slope is going to be minus 20 decibels per decade, and it means that beyond this second corner frequency, there is going to be a line with minus 20 decibels per decade. So go by one decade, come down by 20 decibels, and take a point and connect it. Yeah, you could draw a line with minus 20 decibels per decade. Yeah, that's a small mistake. Here this is, it is written as plus 20, but it is not plus 20, it is minus 20 decibels per decade. So we got the Bode asymptotic magnitude plot for this given transfer function. Okay, fine. Now this is how we get the total plot. Or and in this method, if you want to do, you have to draw all these three Bode plots separately, and then you have to sum them up to get the final Bode plot. You can do it, there is nothing wrong. However, what we can do is, whatever we did in getting this combined or the total magnitude plot, we can compile them as a set of step-by-step procedures, so that there is no need for sketching these plots separately and then adding up. So that's what we are going to do now. We are going to formulate the step-by-step procedure. So what did you do? If you go back, so the first step what we did was, we converted the given transfer function into time constant form. That's what we did. Okay, so transform the given transfer function into time constant form. That's the first step. The next step is separate the terms conveniently. Okay, so as you like, as it is convenient to you. So this is what is the convenient way I did, and of course I believe this should be the convenient form for everyone. And the third step is to find out the corner frequencies. Okay, because the corner frequencies are very important, because corner frequencies are the frequencies at which the slope is going to change. So if I take the first term, it is going to be a straight line everywhere throughout the frequency range, and therefore no corner frequencies associated with an integrated term or a differentiated term, or the terms with poles at origin or zeros at origin. The corner frequency is not applicable, no corner frequencies. So for this, the corner frequency is 1 by 0.5, which is equal to 2. And here the corner frequency is going to be 1 by 0.0125, that is equal to 8 radians per second. So if you look at this, you should be very clear that the term which is having the lowest corner frequency starts contributing to the gain first. Therefore, if I have two different terms, I should consider the term which has got the lowest corner frequency first. For our problem, the first term had the lowest corner frequency, and the second term had comparatively higher, corner frequency. So therefore, we can follow the same order. But let us assume that you have taken this term first and the second term last. In that case, the second term will have a corner frequency of 80 radians per second, whereas the third term will have a corner frequency of, 2 radians per second. So in such case, what you need to do is you have to reshuffle the terms so that they are arranged in the ascending order. So these terms have to be, arranged in ascending order of their corner frequencies. And of course, you can mark these corner frequencies on the, semi-log graph also. So the first corner frequency is 2 and the second corner frequency is 8. 2 and 80. 2 and 80 are marked. What next? And you have to find out the slope contribution by each term also. So of course, this is going to contribute a slope of minus 20 decibels per decade because S term, the multiplicity is 1, and here there is only one pole, and therefore it is again, since it is pole, occurring in the denominator, it is going to be minus 20 decibels per decade, and the slope contribution by this term is going to be plus 20 decibels per decade. Okay, so that's the fifth step. Then the sixth step is starting, you can start plotting the or sketching the magnitude plot. So what we found was up to the corner frequency, first corner frequency, the contribution is from the first term alone. Otherwise, the contribution is due to, the constant gain, the integrator, or the differentiator terms. So therefore, how you can start is, before this corner frequency, whichever terms are going to contribute, for those terms, you need to draw the Bode plot. So obviously for our case, this is what is the, term which is going to contribute before this first corner frequency. And therefore this is going to be a line, straight line through 1, 20 log K with a slope of 20 minus 20 decibels per decade. Yeah, it is drawn. This you should be familiar. This is the contents of essence of lecture 1, otherwise Bode plot part 1. Now, between the first and second corner frequencies, the slope of the line is going to be the net slope contributed by the first and second terms. That's what we saw, right? So the first term contribution, slope contribution was 20 minus 20, and the second term contribution is also minus 20. So the net contribution is minus 40. So therefore, what you can do is from this point, from this corner frequency, draw a straight line, with a slope of minus 40 decibels per decade. That's it. Then what about the frequencies greater than this second corner frequency? Yeah, from the second corner frequency, the third term is also going to contribute, and therefore I have to take the slope of all this. Minus 20 plus minus 20 is 40, and with that 40, you have to add the uh, slope contribution by the third term, then it is going to be minus 20 decibels per decade. So from starting from this second corner frequency, you have to draw a straight line with a slope of minus 20 decibels per decade. Now, so here is one straight line starting from this, starting from the second corner frequency, this one. So we can, erase all the extended parts of the lines, and you can get the combined Bode plot. Okay, And if you have further terms, of course, you need to proceed in the same way till all the terms are considered. Now, just remove the unnecessary parts in the line, and you get the Bode plot, Bode magnitude plot. So whatever I said, can be uh, it can be put in a table also. So here is the factors in the ascending order of their corner frequencies. Corner frequencies are written here. The slope contribution is given, and the net slope is this. For the first row, the net slope is whatever slope we have. It is minus 20 decibels per decade. And for the second term, the net slope is going to be, minus 20 minus 20. These two together, that's minus 40. And this minus 40 plus this plus 20 is going to be, minus 40 decibels per decade. That's what the net slope here. And this line is valid up to the first corner frequency, and that's the frequency range. This is valid up to 2 radians per second, and this line will be passing through 1 comma 16.48. 16.48 is nothing but the 20 log k. And the second line with a slope of minus 40 decibels per decade is valid from 2 radians per second, first corner frequency to the second corner frequency. And this line is valid for all frequencies greater than the second corner frequency, from this frequency to infinity. This line will keep on going like this. Now what is left out is the phase plot. So we know this is the transfer function given, and it is written in time constant form. And of course g of j omega is this, and you need to find out the angle of g of j omega. Of course, angle of g of j omega is nothing but the angle of this plus the angle of this plus this angle of this. Okay, yes. So what's the angle of this? This angle of this minus this, that is the constant, by minus angle of j omega. So angle of j omega, how do you find? It is b by a, tan inverse of b by a. This is b, okay, and a is 0, real part is 0. Therefore, 0 minus tan inverse of omega by 0, that is tan inverse of omega by 0 is infinity, and therefore you will get minus tan inverse of infinity. And similarly, the angle contribution by this one is equal to 0, and this is also 0 minus tan inverse of 0.5 by 1. Likewise this. So you get the expression to find out this angle of g of j omega. Okay, please note, since this is in the numerator, so we get the plus sign, positive sign here. And for other two, you know, yeah, there is again a small mistake. Yeah, it is corrected. So it is not tan inverse of omega, it is tan inverse of infinity. Of course, tan inverse of infinity is 90, and this entire term is going to be minus 90 degree. So what you have to do is you have to take different values of omega, okay, different values of omega, and calculate the angle of g of j omega using this expression. So the starting value should be always 0, and the ending value should be always infinity. Okay. If I put 0, tan inverse of 0 is 0, tan inverse of 0 is 0. So then this term alone will exist, that is minus tan inverse of infinity is minus 90 degree. And similarly for infinity, this is tan inverse of infinity, this is tan inverse of infinity, this is plus 90 and this minus 90, both will cancel each other. What will remain is only this minus 90. So that is how I get this minus 90 here. For all the intermediate frequencies, you can substitute the value of omega here in this expression. You can use your calculator to, get these angles. Please note your calculator should be, in degree mode. Otherwise, you will get all the angles in radians, which you may have to convert it to degrees later. Also, please note that at least, two values in a decade are taken so that you get a better graph. I have taken 0.1 and 0.3, 1, 3, and so on. Why I have taken the third division is in a semi-log graph, usually the third division comes at the middle, almost middle. Okay, not exactly at middle, very close to the midpoint. So that's why I have taken 0.3, 3, 30, and 300 and so on. So once I make this table ready, I can take appropriate scale in the y-axis and I can mark these points. Okay. Once I mark these points, I can connect it by a smooth curve, and this gives me the phase plot. Usually you can sketch a asymptotic phase plot also, but we don't do that. See, one thing you may have to understand at this point is why we sketch this Bode plot like this. Nowadays, nobody is going to sketch the Bode plot by hand. There are umpteen number of softwares to generate the Bode plot of any transfer function. Okay, but still in academic exercises, we do sketch the Bode plots manually. The purpose is only if we learn the Bode plot, sketching it manually, we will be able to understand the Bode plots traced by the softwares. That is one point. And the other point is the main application of this Bode plot is the system identification, in which we will have the Bode plot and we may have to get the transfer function back. We have already seen in the previous lectures that to generate the transfer functions from the Bode plot, only the magnitude plot is sufficient, not the phase plot. So, therefore, if I have an asymptotic Bode magnitude plot, I can get the transfer function of the system easily. So that is why we focus more on the asymptotic magnitude plot rather than the phase plot. Okay, so we don't draw the asymptotic phase plot, we draw the exact phase plot, whereas the magnitude plot is going to be an asymptotic magnitude plot. Yeah, so we completed the first problem, and this is going to be the magnitude and the phase plots together. So with this set of procedures, step-by-step procedures, now we are going to solve the second problem. So this is the second problem. The only difference here is, instead of integrator, we are having a differentiator here, and the order of the differentiator is 2, or we are going to have the two zeros at the origin, which corresponds to this s square. And the other difference is we have got a quadratic term here. If you encounter any quadratic form, you have to ensure whether this quadratic term is going to result in complex pole or the real pole. How do you do that? You have to find out the zeta value. How can you do? Obviously, this is in pole 0 form, and therefore you have to compare with this s square plus 2 zeta omega ns plus omega n square. So omega n square is equal to 20, omega n is equal to root of 20, and 2 zeta omega n is equal to 21, and therefore zeta is equal to this. Obviously, this is a value greater than 1. So which means that this quadratic polynomial will not result in complex poles. It is going to result only in real poles, and therefore this quadratic polynomial can be factorized, okay, with real poles. So if I factorize this is what I get. S plus 20 into S plus 1. I have already got an S plus 20 here. So when this combines with this, s plus 20 the whole square and s plus 1, if this theta value had been lesser than 1, then obviously this is going to contribute complex poles, and I cannot factorize with real poles like this, and this term has to be taken as it is following the principles what is taught in Bode plot part 3. Okay. Now this is the transfer function. Given transfer function is written in this way. Obviously it has to be written in time constant form. Take 20 out of it, be cautious. This is a, uh, power is 2, and therefore when I take 20 out, I have to take 20 square. Okay, then it is 1 by 20. This is already in 1 plus st form. The constant is already 1. So, you need not disturb this term. You can leave as it is. Okay, now this 40 by 20 square is 0.1, and this is the transfer function in time constant form. And what is the next step? Of course, you need to find out you need to, write this transfer function in a beautiful way. Yeah, I wrote it. Okay, so this term I group together because this is k s power n form, which I am already familiar with. This is k by 1 plus ts the whole power n form, and this is also in the same form. Okay, so now I can make use of this. Now it is necessary to find out their corner frequencies. The corner frequency associated with this term is 20 radians per second, and the corner frequency associated with this is 1. So how do you get? This is t is equal to 1 by 0.05, and therefore corner frequency is 1 by t, and it will result in 20. Whereas here the value of t is equal to 1, and 1 by t is 1 radians per second. Obviously, the second term is having the lowest corner frequency, and the third term is having the lowest corner frequency, whereas the second term is having the highest corner frequency. Therefore, the order in which you have to take these terms is this takes up the first position, and the second position by this term, third position by this term. So that is going to be the order in which you have to take these terms. Yeah. Let us create this table. This is what is the table I was talking about in the first example. So let us list out the factors. So see in which order I have listed out the factors. The first factor first, then the third factor is written in the second row because that contributed to the lowest corner frequency. Okay, so I have listed all the terms. Now the associated corner frequencies, obviously this is a differentiator which doesn't have a corner frequency. These corner frequencies have been listed here. Now the slope contribution, this is s square, okay, in the numerator. So it is plus 40 decibels per decade, and this comes in the denominator with a multiplicity of 1, and therefore it gives minus 20, and this is with a multiplicity of 2. Okay, so 2, therefore 2 into minus 20 is minus 40. Negative sign because the terms appear in the denominator. Now we have to get this slopes, net slopes. So this is the net slope, the same. Okay, initially it is going to have the plus 40. Then second is this plus 40 plus this minus 20, that is going to be plus 20. And third, this plus 20 minus 40 is going to be minus 20. Super. Now frequency range, and this line with plus 40 decibels per decade is valid up to the first corner frequency, that is 1 radians per second, and it is up to 1 radians per second. And since this is a differentiator, it will pass through 1 comma 20 log k is equal to 0.1. So if I take the 20 log k for that, I will get minus 20. So that's what is written. So it will pass through at 1 radians per second. The value is going to be minus 20 decibels. And this line will pass through it's valid up to 1 radians per second. And the line with the slope of plus 20 decibels per decade is valid from 1 radians per second to second corner frequency, that is 20 radians per second. And the third line is valid for all frequencies greater than the second corner frequency. Okay, that is beyond 20 radians per second, the line is going to have minus 20 decibels per decade slope. Yeah, the table is repeated here, and we using this table we are going to sketch the magnitude plot. I have marked the corner frequencies. Better you draw a vertical straight lines like this so that you identify various regions. The first is a straight line with plus 40 decibels per decade, and it passes through 1 comma minus 20. Okay, so draw a line with 40 decibels per decade slope and passing through 1 comma minus 20 drawn. Okay, please note, even though I have drawn an extended straight line, this straight line is going to be valid only up to this corner frequency. We can remove the unnecessary part later. Now the second line is from 1 to 20 radians per second. The slope is going to be plus 20 decibels per decade, and it is going to start from this first corner frequency. Yes. Okay, done. And the third corner frequency, sorry, from the second corner frequency onwards, the third line is going to have minus 20 decibels per decade slope. So that is valid from this. Okay, yeah, how do you draw? So if you want to draw a 20 decibels per decade line, go 1 decade, go up by 20 decibels. Take a point, connect this point, and extend this line the same way. Okay, so here you have to come down by 20 decibels. Now you can, erase all the unnecessary parts and get a complete asymptotic Bode plot. That's it. Now it's time to phase plot. Yeah, this is the transfer function. This we know, g of j omega, angle of j omega, g of j omega is angle of these individual terms added together. Okay, and this is a negative real number, and therefore the slope angle contribution is going to be 180 degree, and this is it is having a multiplicity of 2, and therefore 2 will come here. Please refer Bode plot part 2 lecture for these explanations. You can just see the explanations there. So when this expression is ready now, please note this is these two factors are lying in the denominator, and therefore both will have a negative term. Negative. However, this is a positive. It is appearing in the numerator, and therefore you get a 2 times 90 degree, 180 degree. Fine. So once this expression is ready, as we did before, you can calculate the angles for different values of frequency omega. So again, as I said, you have to start from 0 and end at infinity. So this table, if the table is ready, I can just simply plot the points, mark the points, and connect the points to get a smoother phase plot. So this is the magnitude and phase plots of example 2 together. Yeah, so of course you also will be drawing both the magnitude and phase plots on the same graph sheet, semi-log graph. So having understood 2 examples, I'm going to give another example as an exercise. This is what is the transfer function for which you need to draw. I have given the solution here. Please try working out. A few things I would like to explain, some basics or preliminaries for this problem. Please note that it may look like there is no constant term here, but it is not so. You have to convert this to time constant form. When you do that, when you take all these numbers outside, you will have this constant. So therefore, first thing is you need to write it in time constant form. That's one thing to mention. And the other thing is there is no differentiator or the integrator. Okay, so therefore, up to the first corner frequency, the slope is going to be 0 decibels per decade. Okay, since there is neither differentiator nor integrator. So you will have only a gain here when you convert this to time constant form, and the gain can be that k value can be converted to decibels, and you will get it as 62 decibels there approximately. Okay, so up to the first corner frequency, it is going to be a straight line, horizontal straight line at this 20 log k magnitude, okay, up to this first corner frequencies. Okay, so maybe in the first row, what you will have is only the constant. So I'm just talking about this table. Yeah, if you prepare this table, the first term factor is going to be, only the magnitude, and the corner frequency no, and the slope contribution is 0 because this constant gain doesn't contribute any slope, 0 decibels per decade. So that is the point to note. So otherwise, if you follow whatever was taught, whatever was explained in the previous examples, of course, you'll be able to do this. Please try. I will request you to really try practicing this problem. And if you come across any doubt, you can post them in the comments. And I will be really, happy to answer your queries. Thank you.